All right, let's talk about fuels. First off, a little bit of review. So, back when we started talking about reciprocating engines, we talked a little bit about aviation fuels. You talked about this in airframe and general, so this should not be new by any stretch of the imagination. But we're going to do a little bit of review because it's important anyway to know exactly what we're talking about. So, first off, by means of review, we have a couple terms that we need to be familiar with. The first one is stoichiometric mixture. So, stoichiometric mixture, the stoichiometric value, is the ideal combination or ratio of air to fuel by weight to support combustion. So, this happens to be 14.7 pounds of air to 1 pound of gasoline or fuel that we're burning. Now, what that looks like from a more scientific standpoint, a chemistry standpoint, is our gas and fuel mixture looks like this. We have a string of hydrocarbons over here. In this case, we're looking at gasoline, which is C8H18, and we have our oxygen molecules. Now, remember, the air that we breathe is actually a relatively small percentage of oxygen. It's like 20 some odd percent oxygen and over 70% nitrogen. It's technically speaking a compressible fluid, which I know that we've spent time saying that fluids aren't compressible, but that's what it is. I don't know what to tell you. Anyway, we have our string of hydrocarbons and we have our oxygen molecules that have been extracted from the air. When we introduce enough heat to break those molecular bonds, they separate, releasing a considerable amount of heat, but they also recombine to produce other things. We get about 16 molecules of carbon dioxide, we get water that's produced as well, and we're going to get carbon monoxide that's produced from that fuel combusting. But that's what we're looking at. 14.7 is about the perfect ratio. Now, gasoline is pretty flexible. It can burn at a mixture as lean of 18 pounds of oxygen to 1 pound of fuel, or it can be as rich as 8 pounds of oxygen to 1 pound of fuel. But either way, we get outside that limit and it can no longer support combustion. It just doesn't have it. Now, interesting things happen as we go either direction. If the mixture is too rich, then we wind up with is extra carbon atoms that are just floating out in the ether because they don't have a partner to pair off with because we've consumed all of the oxygen in the mixture. So what that shows up as in the stream of exhaust is black soot. It'll be deposited on the carbon on the spark plugs. It'll be deposited on the exhaust system. You'll actually see it exiting the edge. That is just excess carbon because it's a rich mixture. Now on the flip side, when we have a lean mixture, we don't see any visual indication like black smoke, but something interesting does happen. Because of the lack of oxygen, it actually slows down the combustive process. When we slow down the combustive process, it has an effect on the engine that it's operating in, largely because the fuel air mixture can still be burning as it exits the cylinder and goes into the exhaust system, which causes some other problems that we'll talk about in just a minute here. But by way of review, that's what we're looking at. We have our stoichiometric value of 14.7 to 1, which we summarize in most cases as 15 to 1 because it's just a whole lot easier, let's be honest. All right, moving on from that, we're going to talk about something else that's really important about fuels, and that is vapor pressure. Now, we can talk about this in two different capacities. We have just plain old vapor pressure, which is the amount of pressure acting from the column of air on the atmosphere on the fuel to keep it from effectively boiling off and evaporating. We do release some fumes and vapors when it's just at rest, but this is ultimately what we're talking about is that transitional phase that prevents it from completely turning into a gas. Reid vapor pressure is a more specific way of measuring that because Reid vapor pressure is the same measurement taken, but at 100 degrees, I believe, Fahrenheit. Yeah, Fahrenheit. I had to think about that for a second. 100 degrees Fahrenheit. And so we have a specific measurement at a specific temperature. So the reason that this is important is because fuel inside a line can turn into vapor, which causes a problem. What we're really trying to avoid is a terrible thing called vapor lock. And vapor lock is a bit of an issue, especially for an airplane. I'm going to tell you why. As you remember, I just said we have that column of air that's pressing down on us all the time. We have a couple magic numbers that are associated with this. So here is a poorly drawn little stick figure, and up above we have this entire column of atmosphere that is weighing down on this particular individual, poor guy or girl, right? That pressure that's weighing on this individual at sea level is about 15 pounds per square inch. The reason this relates to vapor pressure is if we have a fuel with a vapor pressure of greater than 15 psi, that means at sea level, that vapor pressure is going to be such that the fuel will evaporate at sea level, right? That's the issue that we're dealing with. If it is 15 psi or lower, then it will not. Now, two things can change that. We know that if we adjust the temperature of something, then it can cause it to change state from a liquid to a gas, which that means if we happen to have 15 pounds of vapor pressure or 15 pounds of pressure on our fuel on a day that's, say, 65 degrees, and it is stable at 65 degrees, that's fine. But if we raise that pressure considerably, or raise the temperature considerably rather, then that is going to lower the effective pressure. So it's going to be able to turn into a gas at sea level, right? Follow me so far? So here's what we're looking at. This read vapor pressure comes in to be very important because it's a standardized measurement. The reason we have these two magic numbers here, 5.5 and 7 psi, is because that is the range for most aviation fuels where they will be stable and not turn into a gas. About 5.5 psi to 7 psi read vapor pressure. So that's at 100 degrees Fahrenheit. Now you may think, yeah, that's pretty good. 100 degrees Fahrenheit is great. When is fuel ever going to get to 100 degrees Fahrenheit? Well, it probably won't, unless it happens to be under the cowling close to the engine. And this is why when we talk about vapor lock, one of the situations that we point out quite frequently is after an airplane is landed, right? So the airplane comes in after a nice flight, it is landed, right? This is going to be a poorly drawn airplane. Don't know why I need a drawing of an airplane for this, other than the fact that I felt like drawing one, but hey, you get to watch it anyhow, so that's a whole lot of fun. So we have our airplane sitting right there perfectly happy. Now, as time goes on, the airplane is at rest. All that heat that built up from the engine, which could be well into the 200s or 300s degrees Fahrenheit, is building up underneath the cowling and is getting warmer and warmer. So if we have any fuel lines that are running over the top of the engine, trapping in heat, then there's a very good chance that our fuel temperature is going to get over 100 degrees Fahrenheit, which even if we happen to be sitting at sea level, if the fuel temperature gets high enough, it is going to turn into a gas and it results in vapor lock. And vapor lock is effectively when we form a gaseous format of fuel within the lines that are running through the system. And as we know, most pumps are going to work a whole lot better at pumping liquid gas than they are at pumping vaporized gas. So it can create effectively a block in the system. It can actually cut off fuel flow to the engine and stop the engine in flight, or it can make it very, very difficult to start the engine once it's on the ground. Now, you may have wondered why I just said in flight. Well, here's where this whole column of air thing comes in. As the aircraft gets higher and higher, so as we travel up higher into this column of air, we have less and less weight pressing down. What we see that as is lower atmospheric pressure and lower density. The density will come in here in a minute, but that lower pressure is important. Once we start getting lower and lower pressures, combined with high temperatures underneath the cowling, then we can end up in a situation where the fuel would want to vaporize and create a vapor lock. This is a very important reason for why aviation fuels are approved to use in airplanes and automotive fuels are not. Specifically because automotive fuels have much higher vapor pressures than aviation fuels do, which means it may work fine at sea level, but once the aircraft is in the air at altitude and the air starts to become thinner, we end up in a situation where automotive gas just can't deal with it. The vapor pressure is not sufficient for the altitude we're flying at and is going to vaporize and vapor lock, and it can stop the engine dead in its tracks as it's flying, which is not what we want. Now, you'll notice I did mention density as well. That density is important because when we look at something like, say, a reciprocating engine, you'll note that it takes air in, compresses it, heats it up, and spits it back out. It's effectively an air pump. Now, the thing about that is that the cylinders never change size. They have their total displacement, and that's it. So as the aircraft gets higher and higher and the air gets less and less dense, we end up in a situation where the engine can't take in additional air to compensate for the lack of density because the cylinders don't change size. It's as simple as that. And that's why we use things like turbocharging systems to increase the density of the air entering the engine, because we can't change the volume of air that the engine can take in and put back out. That's that volumetric efficiency that we talked about before. Now, this is all kind of important because obviously, as an aircraft flies through different ranges of altitudes, it's going to need different things that allow it to function. This whole issue with vapor pressure that we're talking about here is one of the reasons why we use things like boost pumps in an aircraft fuel system to help avoid any issues with vapor lock. If we did start to form vapor in the lines, the pumps rather will create a positive flow of fuel all the way through the fuel lines, all the way to the fuel metering device that happens to be putting fuel into the engine. And by the way, if we're talking about fuel metering systems and fuel systems, the line of demarcation for an aircraft between the airframe fuel system and the engine fuel system is typically going to be where the fuel enters the fuel metering device or something directly connected to the fuel metering device. So if we happen to have an engine driven pump that's attached to the engine, a lot of times that will be considered part of the engine fuel system, and that's where that starts. Anything before that, so selector valves, strainers, pumps, indicating systems, all of those, for the most part, are going to be considered part of the airframe fuel system. That's important to know because that's going to tell you which license you're using effectively when you're making adjustments or repairs to an airplane. So, how's that for some extra information? You got to love that. On the topic of fuel meters and altitude, when we schedule fuel into an engine, it needs to take a couple things into effect or into account. We need to know how much air is moving through the engine to schedule the appropriate amount of fuel to maintain our proper mixture. And we also need to be able to compensate for the density of air flowing through that fuel metering device. Now, there's a couple systems that we'll talk about a bit later on about how these fuel meters actually work, but what I want to focus on is how all of this relates to fuel mixture. Now, aircraft engines have a distinct uh, differentiation from automotive engines in the fact that we have the option to control our fuel mixtures, which is actually kind of cool because we have the ability to lean or enrich in the mixture manually depending on the altitude that the engine is flying at and what the requirements are. So what we're looking here is a fuel air mixture chart, and this is actually talking about best power and best economy. And I want to explain these two terms to you because they're actually kind of important to know. When we look at the way an aircraft operates, one of the most important things we have, especially in the world of reciprocating engines, is this guy right here, the EGT, the exhaust gas temperature gauge. Because what it lets us know is basically what our fuel mixture is burning inside of the cylinders. And that's pretty important. You'll hear a lot of pilots throw around jargon like LOP or lean of peak. And the reason they talk about that is it's all about playing this game about getting the best fuel economy against the best operating conditions for the engine. Now, reciprocating engines in aviation are a little bit funny. When they aren't directly injected, and due to a couple other factors, the way that the intakes are built and things like that, our stoichiometric value actually isn't the best ratio of fuel air to operate. In most cases, a ratio of around, say, 12 to 1 is more efficient for those engines. Part of it has to do with the fact that we're going to lose some of the fuel that enters the airstream before it gets out to the cylinder. So running a little bit rich is actually going to help us produce more power because by the time the fuel and air get to the cylinders, it's going to be closer to a best power range of fuel to air mix. Now let's take a look at the way this works. It's actually pretty interesting. You see right here, we have a couple different lines that indicate percentage of throttle. So we have 175, 65, and 50%. And these slopes go lower and lower and lower as we move forward. So we're looking at a couple different things. It's a very strange graph, but what we have is we have our exhaust gas temperature, which is what's being correlated over here. We also have on the bottom side our fuel air mixture, which is rich and lean, and we have fuel flow percentage. So that's flow of normal at our peak exhaust gas temperature. When we say lean of peak, we're talking about peak exhaust gas temperature right here. That's why we say lean of peak or rich of peak. Now, the part that makes this interesting is as we look at our slopes here, the more throttle or the more mixture that we put into our cylinder here, the richer the mixture gets as we move this way, it actually decreases our exhaust gas temperature. The reason that this happens is as we go leaner, remember, leaner mixtures will burn slower, which means they're going to continue burning as it exits the cylinder and gets into the exhaust. As a result, it's going to increase the exhaust gas temperatures. The higher our exhaust gas temperatures are, the higher it's going to increase our cylinder head temperatures. And as a result, we can actually overheat and blow up an engine by running too lean of a mixture. And that's why a lot of pilots are afraid of the concept of lean of peak, because they're afraid of blowing up their engines. But there is that very tempting pot of gold at the end of the rainbow, so to speak, of burning far less fuel, which makes everyone a whole lot happier because it's cheaper. So there's a lot of debate that goes on about this, but that's what we're looking at. The gas will continue burning as it gets into the exhaust system and it drives those temperatures up. And we see that reflected in our graph right here. So as we move in the lean direction, back here, we're going to see our exhaust gas temperatures increase until we reach our peak. That is 100% fuel flow. That is our peak exhaust gas temperature. Now, you'll notice that best power is actually a ways up here, where we're producing more horsepower for the air and fuel that we're putting in, and that's reflected in this curve right here. This is our power output curve. You'll notice right here, we reach this almost asymptotic curve right here where we have best power. And if we continue to enrich and past that, we get too rich and we start to dampen the power that the engine can put out. On the other hand, as soon as we start leaning, we lose power. But you'll notice our temperatures are still going up even as we're losing power. And again, that's due to the effect of the delayed burn pattern on the fuel-air mixture. But you'll also notice as we lean back, we get more fuel economy, and we actually get a point where it peaks out here. So we have this percentage of power and economy. That's not something that you always see, but it shows where we peak out. And that shows our best economy range, which is reflected up here in our temperatures. And this is actually the interesting part. As we continue leaning past peak, we start to get less and less efficient in our combustion, which fundamentally you'd say that's not great. But if we're cruising at high altitude or something like that, then we really don't need that much power. In fact, it's probably more detrimental to us to put way too much power out of the engine anyway, because we're just going to burn fuel unnecessarily and put unnecessary wear and tear on the engine due to the operating temperatures. So as we lean back, we actually get to a safer operating range right here, but we also reach this peak of power and efficiency. So we can lean past that peak exhaust gas temperature and we can run lower fuel mixture, which means we're more efficient. We can fly further for cheaper and everybody's happy. And that is all because of this gauge right here, the EGT. That's what makes that possible. When we can monitor closely our exhaust gas temperatures, it allows us to run that lean of peak. It's not really advisable for a pilot to try if they don't have that information coming in, because obviously you have a pretty narrow window to try to grab here to keep the engine from running in a fashion that would cause it to blow up prematurely. And that's not what we want. So that's the basic entrance into what we have for a fuel system. And so along with those basics, and we have a couple different things that we see. As mentioned before, we're going to have things like pumps that help to avoid things like vapor lock. We have strainers that are going to prevent contamination that could cause interruption through the fuel meter. We have the fuel metering device itself, and then we have some way of taking fuel from the fuel metering device to the cylinders, either through an intake system or through a direct injection method, which we'll talk about all of that a little bit later. But hey, that's almost 20 minutes of boring you. I think this is really exciting, but hey, that's my gain and your loss. Hope you enjoyed this part. Take a look at the next lecture where we'll talk a little bit about aviation fuels and basics of fuel systems.